This is SpaceTime Series 27, Episode 87, for broadcast on the 19th of July 2024. Coming up on SpaceTime, NASA's Parker Solar Probe becomes the fastest man-made object ever built. China's Secretive Space Plane releases a mysterious spacecraft into orbit. And what the universe looks like if people could see in radio waves. All that and more coming up on SpaceTime.
Welcome to SpaceTime with Stuart Gary.
NASA's Parker Solar Probe spacecraft just completed its 20th close approach to the Sun. The flyby matched its previous distance record, achieving perihelion at a distance of 7.26 million kilometres from the Sun's visible surface. During this close approach, the probe was travelling at an amazing 635,266 kilometres per hour, establishing the spacecraft as the fastest man-made object ever built. 3 days after the flyby, the Parker Solar Probe checked in with mission managers back at the Johns Hopkins Applied Physics Laboratory in Laurel, Maryland, with a beacon tone indicating it was in good health and all its systems were operating nominally. The milestone also marked the midpoint of the mission's 20th solar encounter, which began on June the 25th and continued through until July the 5th. Parker will now fly around the Sun at the same distance and speed one more time this year on September the 30th, before making the first of three final planned close approaches on December the 24th. At that point, with Parker's orbit shaped by the mission's final Venus gravity assist flyby on November the 6th, the spacecraft will zoom just 6.1 million kilometres above the Sun's surface, and it will be travelling at an unbelievable 1,005,480 kilometres per hour. The Parker Solar Probe's mission uses repeated gravity assists of Venus to incrementally increase its orbital perihelion in order to achieve a final altitude above the Sun's surface of approximately 5,984,000 kilometres. All in all, the spacecraft's trajectory includes 7 Venus flybys over nearly 7 years, gradually shrinking its elliptical orbit around the Sun for a total of 24 orbits. The near-Sun radiation environment is predicted to cause spacecraft charging events, radiation damage in materials and electronics, and communications interruptions. So the orbits will all be highly elliptical, with only short periods of time spent near the Sun. Launched back in August 2018, the mission was designed to trace the flow of energy that heats the solar corona, the Sun's outer atmosphere, and accelerates the solar wind, the stream of charged particles constantly flowing out of the Sun and bathing the Earth and rest of the solar system. Its aim is to see how energy from the lower solar atmosphere is transferred to and then dissipated in the corona and solar wind. It'll also see how the processes in the corona affect the properties of the solar wind in the heliosphere. So, this amazing record-setting mission still has an awful long way to go. This is SpaceTime. Still to come, China's Secretive Space Plane releases a mysterious spacecraft into orbit, and what the universe would look like if people could see in radio waves. All that and more still to come on SpaceTime. China's highly secretive reusable space plane has released another mysterious spacecraft into orbit. The experimental orbital spacecraft, named Sheng Long, or Divine Dragon in Mandarin, has already been in orbit for close to 200 days on this its third mission. The space plane was launched aboard a Long March 2F rocket from the Jiuquan Satellite Launch Center back in December last year. No reliable images of the mysterious spacecraft have ever been released. Mystery also surrounds the spacecraft released by Sheng Long. It's thought to be a sub-satellite designed for proximity and recapture spy manoeuvres. We know similar tests were undertaken during Sheng Long's second flight. This is SpaceTime. Still to come, what the universe would look like if people could see radio waves, and later in the science report, a new study shows Australian dingoes share very little in common with other modern-day dog breeds. All that and more still to come on SpaceTime. Back in 2016, the Murchison Wide Field Array telescope, located deep in the Western Australian outback, showed astronomers what the universe would look like if human eyes could see radio waves. The findings, reported in the monthly notices of the Royal Astronomical Society, cover the amazing research undertaken by the Galactic and Extragalactic All-Sky Murchison Wide Field Array, or Gleam survey. The study produced a catalogue of some 300,000 galaxies. Gleam was a large-scale, high-resolution survey of the radio sky, observed in frequencies ranging from 70 to 230 megahertz, observing radio waves that have been travelling through space, often for billions of years. Astronomers use the survey to find out what happens when clusters of galaxies collide, to see the remnants of explosions from some of the most distant stars in the galaxy, and to find the first and last gasps of supermassive black holes. Gleam was one of the biggest radio surveys of the sky ever assembled. Its lead author, Natasha Hurley-Walker from Curtin University and the International Centre for Radio Astronomy Research, described the findings back then as amazing technicolor. She points out the human eye sees by comparing brightness in 3 different primary colours, red, green and blue. And Gleam does a rather better job at that, viewing the sky in 20 primary colours. That's not only much better than what human eyes can manage, it even beats the very best in the animal kingdom, the mantis shrimp, which can see 12 different primary colours. Large-scale surveys like Gleam are extremely valuable to scientists, and they're used across many areas of astrophysics, often in ways the original researchers never imagined. Completing the Green survey with the Murchison Wide Field Array was also a big step on the pathway to developing the Square Kilometre Array radio telescope, now under construction in the Western Australian outback in southern Africa. Hurley-Walker described the survey as providing a glimpse of the universe that the SKA LOW will be probing once it's completed. And mapping the sky in this way allowed scientists to fine-tune the design of the SKA for even deeper observations into the distant universe.
So Gleam stands for the Galactic and Extragalactic All-Sky Murchison Wide Field Array survey, and it's a radio sky survey covering the low frequency range of the radio, and it covers all of the sky that's visible in Australia. That's about 30,000 square degrees.
What are you looking at?
So because it's in the radio, we're sensitive to high energy processes in the universe like synchrotron. So that is a process which is caused by electrons spiraling around a magnetic field, and they emit in the radio, so we can pick that up. Now, there's a lot of different objects in the universe that produce synchrotron, and the things that we've published is a large catalogue of galaxies that are emitting in the radio.
By looking at galaxies in the radio, in particular looking at synchrotron radiation, is that giving us a better idea of the magnetic fields that pervade, say, our own galaxy, the Milky Way?
Well, what's super cool about these galaxies is that they're located at really high distances. So we're talking millions to billions of light years away. And the reason they're emitting in the synchrotron is because they have supermassive black holes at their centres. And these black holes are accreting matter. The accretion disk has really powerful magnetic fields. These magnetic fields can launch huge jets of plasma into space, and it's those that produce the synchrotron that we then see in the radio. So when we're seeing all of these galaxies at very high distances, we're actually getting a window into the physics at their very centres around these massive black holes.
And what's that teaching you so far?
So the really neat thing about Gleam is that we observe over a really wide frequency band. So we can see both the lowest frequencies of the radio, like the FM band, where your normal radio works, and the kind of high frequencies around the digital TV. And because we observe across this wide band, we actually get a sense of the, in quotes, sort of radio colour of different objects. Now, that colour actually varies depending on the physics of what's going on. So one thing we can tell by looking at these radio galaxies is if they have a kind of blue radio colour, so they're brighter at the high frequencies and dimmer at the low frequencies, then we think that these objects are just starting out, so the jets have just formed, or possibly they're being confined by like a dense medium around them. Whereas if the jets are very bright at the low frequencies and dim at the high frequencies, i.e. they look kind of red to us, we think those jets are really old and the supermassive black hole stopped emitting jets a long time ago. So basically this is like a colour view of the universe that gives astronomers a direct insight into the physics of what's going on in distant galaxies. Because it's so wide, it covers the whole sky, it means that there's always other wavelengths that have been observed in any random patch of sky. So we can use lots of other radio surveys, we can use X-ray surveys, we can use all sorts of other information to pull out things like the masses of supermassive black holes. So I've just said what we can get directly for one specific specific class of objects, but a lot of the power of modern astronomy is pulling together observations from all different frequencies, and then that'll really help us understand the physics. We've averaged about 4 weeks of data to make one massive view of the sky, and so it's very sensitive, it's very deep, it's very well calibrated, but it doesn't really give you much of a window into very fast processes.
Gleam's the sort of thing that will eventually be included in the square kilometre array project at the low end of the frequency.
Yeah, I guess that would be a wonderful ambition. I would love to be that person, in 20 years' time, leading the all-sky SK low survey. That would be pretty incredible. I mean, you'd be talking hundreds of times better resolution, incredible sensitivity, even wider bandwidth. I mean, you would just be seeing tens of millions of radio galaxies. That would be quite stunning.
As you've gone through the data and put this image together, are there any surprises that you've found, things that you've looked at and said, didn't expect that to be like that?
Well, I have a student looking for transient objects, so basically flares from stars or AGN or pulsars, things that might switch on in our survey and then be bright enough that even though we integrated a lot of time, we can still see them, and then they're not there in other surveys. We found a really cool object. We were like, this is exciting. It's here 1 week and it's gone the next. And eventually we worked out that we'd rediscovered Jupiter.
Oh, right.
So it's actually quite bright at low frequencies. It's got this cyclotron emission. Anyway, it's cool, but unfortunately it's not a new discovery. People have known about Jupiter for a few years now, so...
I take it the emissions from Jupiter are coming when Io has eruptions, which are hitting the Jovian atmosphere and going through the huge magnetic fields between Jupiter and Io.
Quite possibly. So there's probably a project in there to look at all of the MWA observations of Jupiter, and then you could see, what's going on Io because of those. And I mean, that would just be another wonderful student project. We are basically swimming in data here. We have loads and loads of data, and we just need bright people to work on it. The thing I would say about whether I found anything yet, I mean, I have found a distant radio galaxy that basically nobody had even thought was a radio galaxy. People thought this was just a normal galaxy with a quiescent black hole. But I was able to see that a long time ago, like billions of years ago, it had an outburst and had produced these really very large jets. But they were so old and so faint and so, only visible at the very lowest frequencies that I was the first person to find those. And that seems to be a whole class of objects which no one's really seen before because existing surveys don't have the sensitivity.
What sort of redshifts that at?
Oh, actually, this one isn't too far away. I think it's around 0.05, so it's a relatively nearby galaxy, which is why it's kind of astonishing, really, that nobody had known this before. So the jets actually are quite large on the sky, and just no one had the right sensitivity to pick them up.
We often talk about all galaxies having supermassive black holes at their centres. Is that what you're finding?
Yes, that's certainly consistent, but we don't know why some of them are active and some of them are not. Our data should help to solve that puzzle. Again, as I say, cross-matching with a lot of other catalogues and try and get a bit more of a window into the different environments that might cause supermassive black holes to switch on and off, and whether they have like a duty cycle, so whether they're on for some time, off for some time. All of these things are things we can help with our survey.
Doesn't that depend on whether or not they're feeding or not?
Yeah, so there are a really great complementary survey that will also help us answer these questions, is the Australian Square Kilometre Array Pathfinder. That's at the same site as the Murchison Wide Field Array, a hydrogen survey of lots of nearby galaxies. And basically that gets you a really accurate estimate of the masses of hydrogen in those galaxies. And then you can see whether that hydrogen is then turning into stars or, whether it's feeding the supermassive black hole.
Watch clusters of galaxies colliding.
Yeah, so that's another thing. So, yeah, as you say, galaxies can form clusters. So if you have, you can have just isolated galaxies, but for instance, our galaxy is in a sort of smallish, it's not quite a cluster, it's more of a group of about 7 big galaxies and then quite a few satellite and dwarf galaxies. But the biggest groups are clusters, and they can have hundreds to thousands of member galaxies. And they have this hot X-ray gas in the middle of them, and loads of dark matter. And when they collide during sort of structure formation of the universe, it's insane to even picture clusters of galaxies colliding, but they do. They form huge arcs of emission, again, in the radio because of the synchrotron emission. And we have doubled the number of detected these arcs from collisions that had ever been seen before. So we've doubled that number, and that's giving us a window into that structure formation. So like I say, the survey, the nice thing about surveys is you can just get so many different kinds of science from them. Yeah, I'm really hoping it's helpful for the astronomical community.
So this is really helpful for, say, understanding galaxy evolution, and also, I guess, seeing the large-scale structure of the universe.
Yeah, so with those galaxies colliding, that's telling you about the history of structure formation. One could trace out the strands of the cosmic web. So if you've seen the Millennium simulation, you have those wonderful filaments of dark matter, and it's postulated that basically as those filaments kind of condense, the gas that's sort of floating through the universe is pulled into those local gravitational wells, and you'll see that at the node of every collection of filaments, there forms a galaxy cluster. But the idea is that the filaments are still there, they're just not quite as dense as the galaxy cluster. And so along those filaments, there'll be gas that's sort of falling inward. And the idea is that gas can produce shock waves, which again produces synchrotron. I love this process, it's everywhere in the universe. And then we could actually detect that, and so we could see the strands of the cosmic web laid out in the radio. And of course, this measurement is extremely difficult, and the signal is expected to be very faint. But this is the right instrument to do it with.
That's astronomer Tasha Hurley-Walker from Curtin University and the International Centre for Radio Astronomy Research. This is Space Time. And time now for another brief look at some of the other stories making news in science this week with the Science Report. The battle of weight loss drugs is heating up. A new study reported in the Journal of the American Medical Association claims that tirzepatide, commonly sold under the names Mounjaro and Zepbound, does a better job of cutting the kilos than semaglutide, commonly sold under the names Ozempic and Wegovy. The authors investigated the effects of close to 20,000 people taking either of the two drug types. They found that while most of them would go on to lose 5% or more of their body weight, the effects were far greater with tirzepatide. A new study claims that ancient Australian dingo DNA shows that modern dingoes share very little ancestry with modern dogs of other breeds. A report in the Journal of Proceedings of the National Academy of Sciences looked at the pre-colonial genetic landscape of dingoes free from any mixing with modern dog breeds. The authors found that dingoes arrived in Australia more than 3,000 years ago, most likely transported by seafaring people. They found dingoes have very distinct regional populations split roughly along the Great Dividing Range long before the European colonisation of Australia and certainly predating the dingo-proof fence. The DNA analysis also showed less interbreeding between dingoes and modern dogs than was previously thought. That confirms that today's dingoes retain much of their ancestral genetic diversity. In fact, the ancient genomes revealed over 2,000 years of dingo population structure, with Kagari dingoes found to be the purest, with virtually no domestic dog ancestry at all. The study found that behaviourally, genetically and anatomically, dingoes are a distinct species, very different from domestic dogs. New researchers found that people who invest in cryptocurrency are more likely to hold non-mainstream political views and more likely to engage with fringe social media. The findings, reported in the journal PLOS ONE, are based on a survey of over 2,000 people in the United States, 30% of whom owned or had previously owned cryptocurrency. Asking questions about their beliefs, media and personalities, the researchers say crypto investors were more likely to believe in cryptocurrency theories, supporting political extremism or non-mainstream political ideologies, and having dark personality characteristics such as narcissism, Machiavellianism, psychopathy, and even sadism. The authors admit their results are limited by the fact that the participants assist themselves, and so the study can't directly show that these beliefs are directly connected with the choice to invest in cryptocurrency. However, they say the findings may help us understand people behind the relatively new movement. To quote the immortal Dr. Sheldon Cooper once more,
"There is absolutely no scientific evidence to support clairvoyance of any kind." Which means, no insult intended, that you're a fraud. Your profession is a swindle, and your livelihood is dependent on the gullibility of stupid people.
An American psychic's now claiming that he predicted the death of actor Matthew Perry 3 days before the event. But as Tim Mendham from Australian Skeptics points out, like all premonitions, it's a pretty long bow to draw.
We get stories all the time about people predicting all sorts of stuff which they claim after the fact. See, I predicted it, and when you actually go back and look at what they said, it tends to be a lot vaguer than what they're claiming. In this particular case, this is so vague, it's actually nothing there. There's a claim made recently that famous psychic person who contacts the dead, John Edward, who's a regular visitor to Australia. He is big in America. Apparently it might be in UK as well. He goes around and he talks to the dead and upsets people in the audience who get very sad, etc., when John Edward says, I can see your father, and he's happy where he is, and he says he sends his love. No ghost ever says, I can see your father, he hated you all your life. Anyway, so this was a story where someone said John Edward predicted Matthew Perry's death, Matthew Perry being the actor from the Friends TV show, who died of a drug overdose. This person claimed that John Edward predicted Matthew Perry's death because, and this is the tenuous link, they took a copy of Matthew Perry's biography, happened to take it to this presentation by Edward to give to a friend. Edward then asked, has anyone read Little House on the Prairie? And someone said, oh, Perry, Prairie, that's what he's talking about. And he said, no, he's talking about Little House on the Prairie. But someone then put the link, and then Matthew Perry died a few days later. So the suggestion that John Edward predicted Matthew Perry's death is not exactly reliable, although I'm sure at some stage John Edward will use it as a proof. It's basically what people do, and they find links between disparate things. Links such as one person will say something else will happen, and they'll, through the inventiveness of the human mind, make a connection. People always make connections. It's pretty standard. This is one case like that, where someone had a book about Matthew Perry, and Edward referred to something that sounds like Perry. It's actually prairie, which I'm sure there's a lot of other words. He could have said, has anyone caught a ferry here today?
Or a dairy.
And, yeah, have you seen a ferry lately? Whatever. He didn't say Matthew Perry, but people will find the link there anyway. And
I've never, ever watched an episode of Friends.
Neither have I.
I've never seen an episode of the Kardashians either.
I've seen snippets, and that's enough. So, yeah, no, I've never watched Friends at all, so I really feel left out.
That's Tim Mendham from Australian Skeptics. That's the show for now. SpaceTime is available every Monday, Wednesday and Friday through Apple Podcasts, iTunes, Stitcher, Google Podcast, Pocket Casts, Spotify, Acast, Amazon Music, Bytes.com, SoundCloud, YouTube, your favourite podcast download provider, and from spacetimewithstuartgary.com. SpaceTime's also broadcast through the National Science Foundation on Science Zone Radio and on both iHeartRadio and TuneIn Radio. And you can help to support our show by visiting the SpaceTime store for a range of promotional merchandising goodies, or by becoming a SpaceTime patron, which gives you access to triple-episode commercial-free versions of the show, as well as lots of bonus audio content which doesn't go to air, access to our exclusive Facebook group, and other rewards. Just go to spacetimewithstuartgary.com for full details. And if you want more space time, please check out our blog, where you'll find all the stuff we couldn't fit in the show, as well as heaps of images, news stories, loads of videos, and things on the web I find interesting or amusing. Just go to spacetimewithstuartgary.tumblr.com. That's all one word, and that's Tumblr without the E. You can also follow us through @StuartGary on Twitter, @SpaceTimeWithStuartGary on Instagram, through our SpaceTime YouTube channel, and on Facebook, just go to facebook.com/SpaceTime with Stuart Gary.
You've been listening to SpaceTime with Stuart Gary. This has been another quality podcast production from Bytes.com.